Welcome our broadcast live again. Now we will continue with the third invited talk of our conference. We are honored to invite the distinguished Professor Dr. Mahmoud Fotuhi-FIRUZABAD from Sharif University of Technology as our next invited speaker at the ELECO 2023 conference. He will enlighten us with his presentation titled Building Resilience and Safeguarding Our Modern Society Against Power Outages and Large-Scale Blackouts, promises to offer invaluable insights into critical infrastructure protection. His profound expertise and innovative approach promise to provide a thought-provoking and deeply insightful session. Furthermore, we are delighted to invite Professor Aydogan as the session chair, who will expertly steer this important discussion.
Good afternoon, everybody. I am pleased to start the third speech of ELECO 2023. Before starting the speech, let me give a short bio of Professor Firuzabad. Professor Mahmoud Fotuhi-FIRUZABAD, who became an IEEE Fellow in 2014, obtained his BSc and MSc degrees in electrical engineering from Sharif University of Technology and Tehran University in 1986 and 1989, respectively, and the second MSc and PhD degrees in electrical engineering from the University of Saskatchewan, Canada, in 1993 and 1999, respectively. He is currently a professor of electrical engineering at the department in Sharif University of Technology, Tehran, Iran. He is a member of Center of Excellence in Power System Control and Management in the same department. Professor Firuzabad is the former president of Sharif University of Technology, serving from 28 August 2014 to 18 October 2021. His research interests include power system resilience and reliability, distributed renewable generation, demand response, and smart grids. His scientific activities include more than 670 papers and supervising more than 100 master's and PhD theses. He is the recipient of several national and international awards, including World Intellectual Property Organization WIPO Award for the Outstanding Inventor 2003 and PMAPS International Society Merit Award for contributions of probabilistic methods in applied to power systems in 2016, and the 2014 Allama Tabatai Award. He served as the editor-in-chief of the IEEE Power Engineering Letters from 2017 to 2022. He also serves as the associate editor of Nature Scientific Report, guest associate editor, special issue on electric vehicle charging impacts on power systems, IET generation, transmission, distribution, and deputy editor-in-chief, Journal of Protection and Control of Modern Power System, Springer. He is an IEEE Fellow for his contributions to the application of probabilistic techniques in power system reliability assessment since 2014. Today, Professor Firuzabad will give an important speech, which is one of the popular topics of power engineering society. It will be about resilience and safeguarding. So without taking more time, let me start the session, and I will get your questions if you have and forward it to him, as he is not good in health to attend the session. Thank you very much.
Good morning, ladies and gentlemen. My name is Mahmoud Fotuhi-FIRUZABAD. I'm a professor of electrical engineering at Sharif University of Technology. Today I'm going to talk about building resilience and safeguarding our modern society against large-scale blackouts. Before my talk, I would like to thank the organizing committee of the ELECO 2023 for providing me this opportunity to be with you, and in particular, Professor Dr. Özkan Kalenderli. Here is the outline of my talk today. I will first highlight the importance of electric power systems in modern societies. Then I will talk about new challenges that the power grid is facing, and in particular when facing extreme events and disrupting emergencies. I will next introduce the resilience measures and some resilience enhancing risk management solutions in power grids, which are mainly the outcomes of my past and recent going research. Let's start with the importance of electricity in modern societies. We are talking about the electric power grids, which is the most complex man-made machine designed and built today. The US National Academy of Science, Engineering, and Medicine has named electrification as the first greatest engineering achievement in the 20th century. This shows how critical role the power grid plays in our modern society, even more important than the other great achievements, such as aeroplanes, TV, computers, internet, and so on. The energy landscape in electricity grid worldwide is going through a transformation. Based on the International Renewable Energy Agency report, the renewable energies, which counted for about 20% of global electricity production in 2016, will be able to supply a significant portion of global electricity demand, which is about 86% by 2050. Out of this 86%, we can see here that about 60% will be provided by wind and solar power generation, which is the largest share in electricity generation from renewable sources. We can see here that by 2050, the total installed capacity in the world will be about 20,000 gigawatt, out of which about 6,000 will be from wind and 8,500 gigawatt from solar. So the renewable energies will supply about 2/3 of the world's final energy by 2050. Now we talked about the main infrastructure in any society. It is not really a surprise that the electricity grid is the main infrastructure among all other infrastructure that we have in our society. The interdependence and the two-way interaction of electric power grid with the water networks, communication networks, transportation systems, gas and fuel systems, banking, and emergency services make the power grid as the most critical infrastructure network in our modern society. Taking into account the criticality of power system infrastructure, we know that the electricity is an essential commodity that has no substitute. It is therefore of utmost importance to produce, transmit, and utilize energy in a sustainable manner. In other words, we need to balance the three conceptual pillars of economic growth, social progress, with the preservation of natural environment. Considering the importance of this system as the main infrastructure, we will understand that the managing the risk of this system is very important. At the same time, our modern society, because of its pattern of social and working habits, has come to expect that the supply should be continuously available on demand. That means they are expecting to have the zero risk of such a system. This is not physically and economically possible due to the random nature of system failures, which is generally outside the control of power system engineers. So we need to utilize electricity in an efficient and smart manners. In other words, the power grid, which is sustainable, marketable, affordable, reliable and resilient, and technological. In other words, our system or our conventional system has moved to a smart grid system. So, the traditional power system is changing. We are seeing more and more arrival of renewable resources and distributed generation sources on the generation side, which are connected to the grid through the power electronic interfaces. We are also seeing a large number of AMI, smart meters, smart home appliances, electric vehicles, and automation technologies, which are being introduced in the distribution sector. And at the middle, we are seeing the grid, which is being changed due to the changes in the generation and distribution sides. The grid is now hosting bidirectional flow of power and information, which has additional complexity coming from a large number of sensors and intelligent devices at the substations. So we can call this new ecosystem as the cyber physical smart grid. Now, this smart power grid introduces some new characteristics and a number of requirements and challenges. As an example, connection of small distributed energy resources to the distribution grid, availability of large volumes of data, local energy transactions, high uncertainty in the net load consumption balances and the flows due to the uncertainty in the renewable energies, automation, maintenance, and asset management, need to improve the reliability and resiliency of the distribution systems due to the failures in the components, using electric vehicles, energy storage systems, and their integration into the power grid. Now we'll go to the new challenges that our system is facing due to some extreme events. We will see that the smart electricity grid in general is vulnerable to a range of events, some environmental and weather events, such as lightning, storms, and so on. Some physical and mechanical failures, such as failure of equipments, aging and end of life of some of the components, and finally, cyber threats. So these are the main events which may happen to our system. These events can happen anytime and anywhere in the system and can significantly challenge the operation of the power grid. In the face of any challenge driven by random failures or extreme events, the power grid operation goes through a number of operating states, namely as normal, alert, emergency, extreme emergency, and restorative states. Based on the combination of the statuses of cyber and physical security, all the possible operating conditions of the system can be divided into 4 different states. Secure states, in which both cyber and physical securities are ensured. Alert state, in which the physical security is maintained but the cyber security is violated. Emergency state, in which the cyber security is maintained but the physical security is violated. Extreme emergency, which is both the cyber and physical security are violated at the same time. So this could be one classification of the system operating states when some events happen to the system. At the same time, there are some reactive actions for transferring the operating states from one state to other state in order to restore the security of the system operation. They are designated here as preventive, corrective, remedial, and restorative control. Back to the previous slide, when the power system operating states change, the most unfavorable state is the extreme emergency state, in which where the electricity outages are resulted, and some of them may even cause large-scale blackouts in the system. Historically, the blackouts causes are identified to be weather events and vegetation, faulty equipment or human error, vehicles and accidents, animals, and so on. This table here shows that weather events are the leading cause of power outages, accounting for more than about 40 to 50% of all power outages. This slide somehow categorizes the different events that we have. So the events that challenge the operation of power grid can be classified into 3 groups of known, unknown, and unknowable. The known events, such as random failures of power system equipments, and the unknown events, which are designated as gray swans, which is a symbol for a partially predictable, high impact and rare events. Weather events such as tornado are examples of this category of the events. And some of these events are unknowable, which we call it black swans. A black swan is a symbol for an unpredictable, high impact and rare events. So various events in the electricity grid can be somehow divided into different categories as shown here. As we mentioned, some of these known events are those from random failures of power system components. And like any engineering system, power systems also composed of a large number of components which may randomly fail or fail due to aging and end-of-life failures. We try to prevent these failures with the inspection and also maintenance scheduling. The top curve here is known as bathtub curve, which consists of three different parts: the infant mortality, useful lifetime period, and wear out. So in order to prolong the useful lifetime period, we need to do the system and component maintenance. So such analysis and accounting for these events are typically covered in reliability analysis of the power system. Here I would like to emphasize the role of weather in power system operation. We need to understand that the everyday operation of the power grid is environmentally driven. As we can see in this slide on the left-hand side, the power generation, we are seeing more and more renewable, such as wind and solar, that are somehow weather dependent. Wind and solar availability may change as weather parameters change. Even thermal generating units, sudden changes in the weather parameters will have impact on the availability, efficiency, and capacity of power generation sources. On the right-hand side, or the demand side, the way how we need and use electricity, for example, such as heating or cooling systems, is somehow weather dependent. On the middle side, the network equipments such as power lines, transformers, they are all exposed to open atmosphere, and they will be greatly impacted by any disruption which has resulted from the environment. As you saw, therefore, the everyday operation of the power grid is somehow weather dependent and environmentally driven. While we understood that the operation of the power grid depends on weather and environmental parameters, this figure here shows that the weather events are becoming more extreme. We have been seeing an alarming rise in the frequency and also intensity of extreme hot and cold temperature events over the past decades. In this figure, orange and blue colors represent the heat and cold temperature events, and the size of the circles reflects the size of resulting electricity outages to the customers. Speaking of extreme weather events, this figure here shows the wide range of natural disasters in the US. In 2022 alone, these events has resulted in about $18 billion economic loss. Even the frequency and intensity of these natural disasters have been observed to be on the rise over the past couple of years. As an example, in figure A here, the ice accumulation of several inches on distribution power lines caused these poles to collapse. And in figure B, which is related to the ice storm 98 in Canada and USA, we will see again the same impact. The extreme weather events also impact the physical status of solar panels and power lines, which is resulted in the power outage, as we can see in this slide. Now, other than weather, which was the main cause of power outages, a smarter grid is also vulnerable to cyber attacks. This is a major vulnerability in smart grids, as the smart grid is enabling more digitalizations, addition of new sensors, extensive operation of communication networks. So the cyber attacks are no longer a concept in theory. Let's talk about this fact that why the smart cyber physical power grid is vulnerable to cyber intrusions. As you can see from the right side, the information will be captured from the physical layer through the sensors and a large number of sensing infrastructure. They are transmitted from the physical layer through the communication layer to the control center layer for monitoring, operation, and control decision makings. So the flow of data is from right to the left. With all analysis of the data, the operation commands, such as breaker operation commands, set point changes, ramp up and ramp down decisions, have to be communicated from the control center layer all the way to the physical layer for final implementations. So the existing vulnerabilities in a cyber physical power grid is not only from the physical threats, but also from the cyber layer, and due to the need for massive communication of the data and control settings. These evolving events, therefore, have some unique characteristics in terms of the ability to detect and also the understanding on the causing drivers. The state of knowledge about the extreme events are, of course, different. This figure here displays this considerable variation in the level of scientific understanding of weather and how the frequency and intensity of different weather events may evolve as a consequence of natural variability and climate system oscillations. In addition, these events may have different warning times before they happened or after they happened. The horizontal placement here provides some indication of how much warning time there may be before the event. While in this figure, the vertical axis provides some indication of how long it may take to recover after the event occurs. The lines provide a representation of variability in these estimates. As an example, for an earthquake, The warning time is in the order of seconds, while the restoration time is in the order of days or weeks. So it will make it as a very high impact event. Therefore, the need for resilience is highlighted in the face of evolving events which are rising in frequency and also the magnitude. And so we should be able to answer two main questions. The first one is how we can accurately detect, predict, and prevent such a disruptive event and the consequent electricity outages. And the second question is how we can efficiently plan to mitigate and recover from the electricity outages. Let's now here define the system resiliency. The resiliency can be defined as the ability to efficiently recover from the challenges or disruptive events as fast as possible to minimize the consequences. Resilience enhancement can be approached in both the planning phase and also the operation phase. In the planning stage of the power grid, that we also called here as structural resilience, in which the focus of this stage is grid hardening to make the grid stronger to future extreme events. For example, new investments, increased redundancy, undergrounding power lines, and so on. It can also involve the operation of the power grid in the face of an approaching disaster. And we called it here operational resilience. Here, the disaster is approaching or has happened, and the focus here is to timely restoration and recover the system. For example, having efficient control and microgrids in the system. Analysis of resilience in a power system involves generally multiple phases. Here we defined it in 4 different phases. The first phase is threat characterization, which involves understanding of the events. For example, storms, floods, and hurricanes. The second phase is vulnerability assessment of the system components to the event which has occurred. The event may change over the time also and the space. Of course, different elements in the system has different vulnerabilities over the time. The third phase is reaction of the system, in which the impacts of the event on the system performance will be evaluated. And the fourth phase is restoration and recovery of the system. Because the power system is hierarchical, the same concept apply at several different levels of the system, including at the interconnection, at the region, that some of which are operated by regional transmission organizations, local transmission and distribution systems, and also the end-use level, which is at the customer side of the meter. In this part of the presentation, I'm going to introduce some of the resilience enhancing risk mitigation strategies against evolving events. In general, the risk management strategy involves three main steps. The first one is quantitatively calculate the system risk. And the second step is to determine how the system risk can be reduced. And the third step is justifying an acceptable risk level. So in the risk management, somehow we have to do these three different steps. I'm going here, as I said, to discuss about some of the resilience enhancing risk mitigation strategies. I'm going to talk about 7 different strategies briefly. Investment in microgrids, distribution automation, mobile power sources, operational flexibility, system reconfiguration, maintenance and asset management, and also battery energy storage systems and their integration in distribution power grids. The first strategy is investment and operation of microgrids. The incorporating of distributed generations, energy storage systems, controllable loads, microgrids are all regarded as the key elements of the next generation of power distribution systems. The main and essential advantage of microgrids is their ability to supply local loads in the event of upstream grid outages through islanding operation, which can considerably improve the system performance. So in this context, microgrids can be isolated from the upstream network in case of disturbances and sustain the supply of local loads through optimal management of available resources. Microgrids can be viewed as small-scale power systems with self-supply and islanding capabilities. The question is, in case an extreme event happens or we have some failure in the system components, what would be the adequacy of the system and how the different customers can be supplied? If you look at this slide here, in case of an extreme event or a failure of system components, here we have 2 microgrids. Okay, this one is islanded and this one is connected to the main grid. So what would be different options if an event occurs? Okay, for this case, one solution is to envision the power grid of the future, which made it of some smart and connected microgrids. So the neighbor microgrids can help each other in case one of them is going through some problems or capacity deficiency. Here, upon the occurrence of a contingency event, microgrids may also operate automatically or form a single island in order to assist each other, like we see here in topology 2. So we'll see here that the 2 microgrids, they form in a single microgrid. Moreover, when we have multiple microgrids, they may form a larger island, like here we can see in this figure 3. And based on the agreed outage management of system, they can share the available generation and storage resources to supply the higher priority loads. So we can see somehow we have a dynamic microgrid. That means we had here a smaller microgrid, but now we made it a little bit larger microgrid, so some part of the load in the other microgrid can be supplied with microgrid 2. This figure shows a hierarchical outage management framework, which consists of 2 hierarchical levels. The microgrid center controllers, which are MGCC, located at the lower level, or level 2, they are responsible for operation and management of the associated microgrids, and the distribution system operator has the role of microgrids coordinators at the upper level or level 1. In this framework, distribution system operator is responsible for maintaining the security of supply in the whole distribution system. Therefore, when a disturbance occurs in the upstream network or even within the distribution system, the distribution system operator as an independent entity coordinates the functions of microgrids and also tries to enhance the reliability and resiliency of the whole distribution systems. So this is done by optimal sharing of resources among the microgrids. This slide shows the proposed hierarchical outage management scheme. When an event occurs in the system, the microgrids schedule their available resources and they try to minimize their load curtailment in the first stage of the proposed scheme. Based on the obtained schedule in stage 1, the microgrids determines their additional power or deficit power for the next time step, and they announce it to the distribution system operator. In the second stage, distribution system operator arranges the possible power transactions among the microgrids and utilize the additional power of microgrids resources to cover the unserved demand in stage 1. Therefore, the distribution system operator announces the result of the second stage optimization to the microgrids so that they can adjust their schedules based on the decision made by the distribution system operator. So, based on this discussion, we can confirm that the proposed strategy will meet the requirements of the resilient outage management system. Based on this scheme, the microgrids and the distribution system, they are able to rapidly respond to changes when an event occurs. The second strategy to mitigate the risk, here we defined as distribution system automation. Distribution automation can greatly enhance the network reliability by speeding up service restoration and therefore can significantly reduce the customer outage time. Distribution automation is considered as one strategy to use a high-speed communication system and proper technology to enhance the system reliability by reducing the service interruption time and also the area which are affected by the fault. Moreover, the optimal number and location of switches, the optimal number of location and optimum size of the energy storage systems were also determined to improve the system resiliency against various events. This slide shows how we can model the active and passive failures in distribution system operator, and how we can calculate the system reliability when we want to consider the active and passive failures. The right-hand side figure shows how the fault management activities can proceed with and without employing distribution system automation. The time here also shows that all of the times can be extended further during the storm conditions when the control center operators are managing multiple outage scenarios. Here we see the impact of distribution automation on resilience curve. We already saw the resilience curve and different phases. When a severe event like a hurricane occurs, the network experiences widespread outages during the event. So if measures are not taken in the network to improve the system resiliency, the recovery phase will be in the form of a traditional curve. But now with the automation system and also having energy storage systems, not only the outage time will be decreased significantly, but also the amount of load provided by the network will also be increased. So we can see, instead of this curve, which was the normal curve during when we do not have the distribution system automation, it will change to this part, and the restorative process will be started earlier. The third strategy to mitigate the system risk is mobile power sources. They are more cost effective than stationary storage units, and they come in different shapes and technologies, including battery storage on a truck or mobile emergency generators. They can move around and provide resilience and reliable services to places that we need. So while you are waiting for the repair of the failures, these resources can restore electricity to the customers, and even we can have mobile wind turbines. This slide shows the features of mobile power sources. As I noted, they are more cost effective than stationary storage units. They can deliver resilient services locally and faster also to critical loads and services during the emergency time. They, however, rely on transportation networks. Therefore, pre-positioning and scheduling optimization of these resources are critical, considering both the power and transportation networks. The fourth strategy to mitigate the system risk that we are going to introduce here is operational flexibility. To cover the net load variability and also uncertainty in a power system, using the flexibility capabilities of energy resources is a promising solution. Flexibility in general can be defined as the capability of a power system to make the production and consumption power balance in the presence of the net load variability and uncertainty. Distribution system resources are the main producing of flexibility capabilities. And from their perspective, flexibility is often referred to as the modification of the consumption or generation patterns due to direct or indirect control signals. So the benefit of having sufficient flexibility capabilities goes to both distribution and also to transmission system. Flexibility capabilities of energy resources can be used at both the transmission and distribution networks. At the transmission level, conventional generating units, large customers, they can be utilized by the transmission system operator to overcome the challenges in the transmission networks. However, in the distribution networks, distributed energy resources provide flexibility services to overcome the challenges in the distribution networks and also offering to the transmission network. Due to the increasing penetration of distributed energy resources in modern power distribution systems, most of the researchers nowadays are focusing on the capability of DERs on providing flexibility. This slide shows that how the flexibility can compensate the net load's variability and uncertainty. The aim here is to utilize distributed energy resources flexibility to meet the power system flexibility requirements and also to cover the variability and uncertainty of the load. Here we can see that L0, L1, L2, and L3, these are the variability of the load, and U1 and D1 represent the uncertainty, as an example, at the L1 level, or U2 and D2 are the uncertainty at the L2 level. So we need the upward flexibility or downward flexibility in order to cover the variability and also uncertainty. As I noted earlier, and also according to the resilience definition, rapid recovery is one of the main features of a resilient system. So in order to quantify the speed of recovery in a system, we have to define an index. Among several indices which has been defined for the power grid resilience, one of the recovery metrics demonstrates that how promptly a network recovers to its pre-event resilient state. So as we can see from this figure, the slope of the curve here during the recovery phase is introduced as a matrix here, which is R0 minus RPE divided by TPR minus TR. By the way, the performance index here has been defined as the number of customers which had already been interrupted and then recovered. So this index, which is the slope of the line that connects, does not really accurately describe how fast the recovery is. So as an example, the matrix gets equal values in both cases of A and B here, as shown in this figure. Okay, in general, this matrix cannot describe the speed of recovery precisely. So we defined another index, and the recovery index here defined as the number of recovered customers divided by the average outage time of the affected customers. So the new index actually defines how fast the interrupted customers can be recovered. This slide shows a distribution system which has been clustered into four different areas. And these four different areas are how to dispatch the maintenance crew members in the distribution system. In addition to that, an event occurs so that the line between 23 and 24, 8 and 9, and 2 and 3, the line will be out. So the red ones are the load points which are going to be disconnected. Okay, only we can supply load points 1, 2, 19, 20, 21, and 22. Then using the system reconfiguration, we are able to supply some of the load that you can see those green ones. In addition to that, we have two distributed generators at buses 5 and 16. Okay, in this slide, we assume that the repair time can be classified into different steps of half an hour. So in the 7th time step, the two figures 2, 3, and 8, 9 are repaired, and so they come back to service. So you can see the load points which have been recovered. But still load points 24 and 25 are disconnected. Figure C here shows the load which has been recovered but without reconfiguration in the system, while figure D shows when we have the reconfiguration, and we can see now load 24 is again reconnected, and we have only load 25 which are disconnected. Okay, this figure shows now here the resilience metrics when we have reconfiguration and we don't have. The line, the green line here shows that the difference into resilience metrics when we do not have distribution system reconfiguration, and the red one shows for the case when we have reconfiguration, and it can be seen that the time that the system starts to be recovered in the case of reconfiguration is earlier than the case when we do not have reconfiguration. The next strategy is maintenance and asset management in order to mitigate the risk. As we can see from this slide, we see that we have corrective, preventive, predictive, and prescriptive maintenance, which are various strategies in maintenance of the system. As the system becomes smarter and smarter, we can see that now we're going mainly due to having sufficient data in the system, we'll go for predictive maintenance rather than preventive. So the goal is when you have sufficient data, you can make your system much more reliable due to having more information on the components of the system, and you will do predictive maintenance while you have sufficient data, and this could considerably enhance your system reliability and resilience. This slide shows the three main stages associated with reliability-centered maintenance, or RCM. Even though the RCM has proved its very good metrics in a large number of industries, it has not been yet used that much with the efficient analytical methods in the power engineering context. So when we modeled the components failure rates, an efficient cost-benefit evaluation approach can be proposed and done in a variety of maintenance plans. So it is very important in the case of reliability-centered maintenance to determine the critical components associated with the system. The last strategy to mitigate the system risk that we are going to introduce here is the utilization of battery energy storage system, which is one of the advanced smart grid technologies. And this technology hardens the distribution grid and will result in enhancing the system resiliency during the emergencies by offering additional operational flexibility. The overall scheme consists of 3 steps. The first one is seismic hazard modeling and characterization, in which we estimate the most probable earthquake magnitude at the location of interest using some historical data. We then determine the ground type at the location of interest, and then we estimate the technical attenuation relationship suitably so that we can capture the characteristics or geotechnical characteristics at the location of our interest. The second stage is seismic vulnerability assessment, in which we are going to do is a set of damage states are introduced so that they can highlight the fact that different structures respond differently to the forces, and therefore different level of vulnerability are determined when an event occurs. The last stage is resilience driven by battery energy storage system planning. In this stage, we need to solve an optimization problem so that we can determine the best location and size of battery energy storage in the system so that we can enhance our system reliability. And this slide shows the system transition states when a critical high impact low probability disturbance occurs in the system. We will see that the disruption starts at tau and will continue until TP, which will be here. Then after a preparation interval, which will be TR minus TP, the restorative actions starts to improve the system back to the normal condition, which will be within TR and TR prime. However, figure B here shows the impact of using battery energy storage system, which harden the system against high impact low probability events by providing more flexible system response. We will see now if battery energy storage system is used. It can be seen that not only TR1 shifted here by delta T to limit the disruption time, but also the system performance also would be improved by delta PD. So it can be seen that utilizing battery energy storage system will improve the system resiliency. In conclusion, we talked about the importance of electric power grid as the main infrastructure in any society. We also talked about transforming this system into a smarter grid in which it is more vulnerable with respect to physical and cyber threats. And at the same time, we also introduced a number of strategies which can be used in order to enhance the system reliability and resiliency. Thank you very much for your attention.
So I would like to express the best wishes to Professor Firuzabad on behalf of ELECO Organizing Committee. I also want to express our best wishes to the attendance. By the way, if you have any questions about the presentation, you can direct it to Professor Firuzabad using the given email or to ELECO organization or to myself. We will be pleased to reply you whenever possible. Thank you very much.
We extend our heartfelt thanks to Professor Dr. Mahmoud Fotuhi-FIRUZABAD for his compelling invited speech on modern power systems and resilience against power outages and blackouts. His expertise in smart grid technologies and innovative approach to power grid reliability has greatly enriched our understanding. His contribution to today's session has been invaluable in highlighting the vital importance of robust and flexible power infrastructure in our modern society. Our thanks also go to Professor Aydogan OZDEMIR for his valuable role in facilitating today's session. Dear participants and guests, I hope that the first day of our conference has been an enriching one for all of you. We are now closing today's live broadcast on YouTube. Our sessions will continue via Zoom with topics including energy sources and power markets 1, control systems 1, biomedical electronics and antennas 1. We extend our heartfelt thanks to all our esteemed invited speakers from around the world who have joined us despite the time differences for sharing valuable knowledge that rekindles our passion for science. Please join us tomorrow morning as we resume our sessions at 10. The day will feature two distinguished invited speakers who will discuss valuable and useful topics as well as Zoom sessions with a number of innovative and valuable paper presentations. To conclude today, we will hold a commemoration and conversation meeting in memory of esteemed Professor Dr. Cevdet Acar, whom we sad to lose this year. His contribution to our field were immense and his legacy continues to inspire us all. For session links and detailed conference program, please visit www.eleco.org.tr. Stay with respect and love. See you on our next live show.